Okay. Quick recap of the last couple of days though, before I start. One of the things I need you guys to be fluent in, I think fluent is a good choice of word. I need you to be comfortable working in radians. And it's a totally different way of changing your mind. Just in terms of like how you interpret, like I like this grid as a place to start. That's 0. This is 90 degrees. That's 180 degrees. That's 270 degrees.
Jill Bullock, can you please come to the office? Jill Bullock, please come to the office.
So there, I've just labeled the whole circle there with degrees as well as fractions of pi. And so long as you can get the concept that all the way around the circle is 2 pi, and the reason for that is the circumference is 2 pi r, but like the radius is 1 basically. So if the radius is 1, then that's how many, that's why it's 2 pi radians when you're there. So does that make sense so far? That's your first main thing you need to be able to do. I'd say the second main skill I need you to have is understanding how to use that kind of cast rule and figure out that sometimes you're going to be plotting things in more than one quadrant. You just have to be able to recognize that when you use your calculator, it's going to give you an answer, but it may not give you the answer you were intending for it to give you. If you're in radians, it's going to give you some ugly decimal number, and sometimes we have to use triangles like 1, 2, square root of 3, or 1, 1, square root of 2, to try to figure out whether it's a 60 or a 45 or a 30, which are actually pi over 4, pi over 3, and pi over 6. Maybe not in that order, but does that make sense? And then the last thing we talked about yesterday is that this unit circle kind of concept is really where this wavy graph going up and down kind of comes from. And you can either have the sine graph or the cosine graph, which is just a sine graph that's failed the grade. So that's basically what we talked about so far. My goal today is to be, I just want to be very thorough. The curriculum does not specifically claim that you're going to be asked to know about the graphs of these next 4. But I don't want to take that chance, because it really takes me through, a couple of minutes here just to show you the pictures of the remaining 4 graphs. So just in case it comes up, I want to have shown you these graphs. Does that make sense? So here are the remaining graphs. This is what tan looks like. Tan is kind of a tricky graph in that it has a whole bunch of asymptotes all the time. One of the reasons why that occurs is that tan is normally supposed to be equal to opposite over adjacent, or in our example, we changed opposite to y, and we changed adjacent into x. Does that make sense so far? But we said that if it's a unit circle, technically sine was equal to the y value, and cosine was equal to the x value. So it can actually be written like this. Tan is equal to y over x, y is sine, and x is cosine. What ends up happening is then wherever cosine could possibly have been a 0, you can't divide by 0, so you get asymptotes. Where was cosine equal to 0? You guys have that little manipulative we made last time? I'll just redraw one real quick in case you don't have it nearby. Yeah, it was like every half pi basically. Well, it was half pi, and then it was every pi after that. This is what cosine is supposed to look like. So cosine is equal to 0 at half of pi, and the next time it's equal to 0 is at 1.5 pi, so 3 over 2. This explains then why there's an asymptote at half of pi, and at 1.5 pi, and at 2.5 pi, and at 3.5 pi. So this is what tan looks like. It's basically got an asymptote where it starts from very low, then eventually it reaches 0. Anyone want to hazard a guess as to why it reaches 0 right here? Because that's where sine equals 0. Okay. You know how like tan is now going to be equal to sine over cosine? That's actually, by the way, on your formula sheet somewhere. It'll tell you that tan is equal to sine over cosine. If I want tan to equal 0, that's where sine is supposed to equal 0. And so sine graphs normally look like this. So long story short, everywhere that sine is equal to 0, you get a 0. Everywhere that cosine is equal to 0, you get an asymptote. So a tan graph basically consists of alternating zeros and asymptote. It goes 0, asymptote, 0, asymptote, 0, asymptote. And it does that basically ad nauseum. I'd like to skip ahead. I want to show you guys the cotan graph. It's the last one on here. This one is cotan. Cotan is supposed to be equal to adjacent over opposite, which then is equal to x over y, which means that cotan is actually equal to not sine over cosine, but it's equal to whatever cosine was divided by whatever sine was. All that happens then is the properties flip. There's a whole bunch of asymptotes in the cotan graph, but those asymptotes exist wherever sine was equal to 0. Well, where is sine equal to 0? Sine was equal to 0 at 0 and at pi and at 2 pi. So it does the exact same thing. It keeps alternating asymptote 0, asymptote 0, asymptote 0. Only what ends up happening is the graph, rather than going from low to high, ends up going from high to low. And that's all. So, like I said to start, this is actually not something that typically is expected, but I just want to make sure you've seen this in case it comes up. So, the other two graphs are for cosecant and secant. This one right here should be cosecant of theta. Cosecant of theta is basically the reciprocal of sine. If you took a sine graph and you did like 1 over top of it and you flip it upside down, that's what cosecant is. Right here, sine has a 0. So imagine that 0 is like really like, well, 0 over 1, for example. What if you take the fraction 0 over 1 and you flip it upside down? Can you really do that? So that's why, again, you get asymptotes everywhere that's sine. Here, like the red graph, by the way, is what sine is normally. Wherever sine is 0, the purple graph gets an asymptote. This point right here is another key point. Sine can get as high as 1. What happens when you take 1 and you do 1 over 1? You still get 1. So that's why wherever sine was equal to 1, the cosecant graph is also still equal to 1. And then the last part here, all of these numbers right here are like fraction decimal numbers, like less than 1. Well, if you reciprocal 1 over 2, it becomes 2. If you reciprocal 1 over 3, it becomes 3. And so that's why all of these low values actually become quite large. So the graph ends up having this shape. It does like an upright U, then an asymptote, then an upside down U, then an asymptote. And it basically alternates like right side up parabola, downside parabola, upside parabola, downside parabola. Does that make sense? The last graph is very similar. This is secant. And secant is if you take a cosine graph and you make it go to the -1. Basically, you flip it on its reciprocal. Same principles apply. Wherever a cosine graph was supposed to be equal to 0, you can't reciprocal 0 because that would be 1 over 0. You can't do that. So here's where cosine is equal to 0. Well, on the green graph, that's where you get a bunch of asymptotes then. And wherever cosine was equal to 1, well, that point stays the same. You have the exact same concept. You have an alternating right side up parabola, upside down parabola, right side up parabola. You just keep alternating them. The only difference is, just like with sine and cosine, one of them is just set back half a grade. So just like a cosine graph is a sine graph that's failed a grade, same thing here with secant and cosecant.
Which one is set back?
So here is the cosecant graph. You see how like it starts off right here as its first one? Here's the next one. Normally it would have been right here, but now like it's been shifted back just a little ways. Does that make sense? Long story short, I just want you to know these different graphs. I wasn't going to write in all the properties. I guess we could if you really wanted to, but so long as you're content knowing what those graphs look like, in case they come up. I just want to make sure you've seen them before. Honestly, if you get stumped and you need to relook at one of the graphs, what I would do is I would type in like say sine x. I would put a bracket around all of it and then go to the -1. If you do that, you're going to get a cosecant graph. And it should hopefully have this. Actually, this isn't going to work because my window size is currently going from -1 to 1, but the reciprocal graph is all either way high or way low. So I should probably actually change my graph to make it go from, say, -5 to 5. There, this is better. So now you get this upward section, asymptote, bottom section, asymptote, up section, asymptote, bottom section, asymptote. Does that make sense? I may as well just draw all of them real quick. Or you could do the same thing with, say, tan. This is what a cotan graph looks like. The little swoop down thing, asymptote. Swoop down thing, asymptote. Swoop down thing, asymptote. Actually, there is one thing I should talk about. What's the period of this graph? How long does it take this graph to repeat itself? How far is it from one point to the next point on the graph? Pi, yeah. A tan, yeah. A tan graph has a period of pi. However, this one right here is cosecant. How long until this graph repeats itself? How far is it from here to here? I know it's not in 2 pi. Yeah. Cosecant and secant and sine and cosine, they all take 2 pi to repeat themselves. This one right here also takes from here to here. It takes 2 pi to repeat itself. But any tan graphs, just based on how they seem to work, they don't take nearly as long to repeat. From this point to this point right here is only pi apart. So I should point out, tan graphs and cotan graphs are only separated by pi.
What was the other one?
So everything that is either based on sine or cosine, or secant and cosecant, they're all separated by pi. That's how, 2 pi. 2 pi is how long it takes those ones to repeat. Tan graphs, though, are only pi for them to repeat. So let's try some questions. You should mostly be tested on sine and cosine graphs. I'm not expecting a lot on tan, cosecant, secant, or cotan, but like I said, I just want to make sure I'm thorough. So here's a sine graph. What does normally a sine graph look like? Goes like up and down like that. That's what a normal sine graph looks like. What's happened to this sine graph, though? So we move down 3. That should be the last thing we do, though. What does this k value mean? Yeah, it's going to pull it like up. So I don't know how much higher it's going to get, but it's going to become taller. It's also going to be shifted over a little bit, so it's going to go over a ways. And then it's also going to go down 3. We want to know the range of the function. What does range refer to, x or y? Okay, so in our example, we actually want to care about this one right here. Oh, actually, they're all like that. If it had said theta in between there, that would be domain. So I guess that doesn't narrow it down. So, the k value, is that going to affect the domain or range? Range. It's going to make some stuff taller. What does a sine graph normally go between? 1 and -1. Well, I don't know what this number is. Let's say it was 3. Well, then the graph would go as tall as 3 and as low as -3. Or if this number was 100, it would go as high as 100 and as low as -100. So with this number being unknown and it's k, would it be fair to say that this graph will now go as high as k and as low as -k? Whatever this stretch value is, that's how much it's going to go in that direction. What about this pi minus 3? What does that affect? Domain or range? Domain. Why? It's just sliding the graph over, yeah. So that doesn't actually really mean anything. What does the -3 do? Slides everything down 3. So what should happen is whatever this top number right here is, it's going to go down by 3. And whatever this number right here was, it's also going to go down by 3. So what's going to happen now is your highest number is going to be whatever k was, subtract 3. That's as high as this gets. And your lowest number, it would have been -k, but it's also going down 3. Which answer represents that information? C does. They really tried to mess with you, though. Rather than going minus k minus 3, they went minus 3 minus k, just to kind of screw with you a little bit. And then rather than doing k minus 3, they did minus 3 plus k. That makes sense. Like here, rather than doing k minus 3, you could have written it as minus 3 with a plus k. It's still the same thing, it's just in a different order. And rather than writing minus k minus 3, you could go minus 3 and minus k. So the answer for that one was C. That makes sense. Let's try another one. Here's a graph of cosine, only we're taking cosine and we're shifting it over a bit. We want to try to figure out which graph this will be identical to. You could use your calculator, but we should be able to do this by hand a little bit. What does a cosine graph normally look like? Starts down and then back up again. That'll work. What does a plus pi over 2 mean? Moves it this way. Yeah, that's left. I always have to do this, by the way. So moving this over here, if I slide everything backwards a little bit, that means you're going to have this point here, this point here, this point here, that point here, that point here. So your graph would look like this now. That's actually going to be B. That's going to be negative sine. How does sine normally look? Normally it looks like this. Can you visually see, though, how it's been flipped upside down? Normally sine is supposed to go up, down, down, up, down, further down, up. Can you see how this new graph is going down first and then back up? This graph in red right here is a negative sine graph. It's a sine graph that's been flipped head over heels. If you had to, I guess what you could do is you could type all 5 graphs. You could type this one in your calculator, type in all 5 of these graphs in, and just see which ones are the exact same as each other. That makes sense? Okay, this was an old diploma question. Like I said, I haven't seen them do a lot with cotan and secant and that stuff, but I'd like you to know it. So the question here now is, what's the domain of a cotan, but you throw a 4 inside of it? What is cotan's domain normally? No, it was just every pi, actually. Tan and cotan repeated every pi. So that's normally, it repeats every pi. What does a 4 do, though? Squishes everything in. So now your domain will be pi over 4. Does that make sense? Well, that's actually not the question here, though. The question is, what's the domain of this graph? So I'm just going to kind of go back to the picture here. Here's cotan. Where are all of my asymptotes? Where's the first asymptote? There's one at 0, actually. Then there's one at pi. Then there's one at 2 pi. So what's going to happen to all of your asymptotes when you squish it in by 4? This one will be at pi over 4. That'll be 2 pi over 4. Does that make sense? So basically, the domain can be anything except for the fact that you can't have pi and 2 pi and 3 pi. Well, now you can't have pi over 4, 2 pi over 4, 3 pi over 4. So which answer best represents that? Yeah, A. This basically means a cotan graph can have any numbers you want. This is a really ugly cotan graph, but if you get the idea. But there are a few exceptions. Where are those exceptions? Well, every pi over 4 n times. You can't have those because those are where asymptotes show up. So that's pi over 4. This would be 2 pi over 4. This would have been 3 pi over 4. This would have been 4 pi over 4. All because you squished it in. That makes sense?
Wait, sorry.
Okay.
N one, that's the one you can't do?
Say that again?
Like the one with N?
Yeah, I just put an N there, just meaning that you can't have it here or here or here. The N just refers to, like, we don't know how many times you're repeating this, but like you can't do it for the first pi over 4 or the second pi over 4 or the third pi over 4. That N just means that you keep going around the circle over and over and over again. Okay, this one's probably one of the more challenging ones. I'm going to give you a second just to read it first, because you got to interpret some graph notation first. Hopefully you'd agree that there's two different graphs. There's some sort of sine and cosine graph. I don't actually know what the equations are. There are a couple of points that are labeled for you. This has been labeled as point A. It's where the graphs cross. Does that make sense? And that coordinate there would have been K, comma, M. Because the X value is K, and the M value is, or the Y value is M. Does that make sense? And basically the question just asks you which of these four statements is true. So let's walk through them one at a time, see if we can find a statement that's true. F of X is G of A. There's a problem with that. A itself is just what we're referring to as the point, but A is not actually an X value itself. Does that make sense? The X value itself has been represented as K. So like G bracket A doesn't even make sense because A is just referring to the both sets of points. So it clearly can't be A. All right, next statement, G of M. Right off the bat, that doesn't even make sense. G bracket M, the thing you put in brackets is supposed to be an X value. But M is the Y value. So that doesn't even fit. F of M. Again, the thing in brackets is supposed to be a X value. But the X value is K, not M. Does that make sense? So that's not a statement that fits. Okay, here's one that might work. F of K. Can you do F of K? F of K means what is the Y value when the graph is K? K is a number you can plug in. What is the Y value at that point? I would say it's M. Does that make sense? On the first graph, if you plug in K, you get back M. So that's supposed to be M. What's G of K going to be? Actually, it's also going to be M. On the G graph, if you plug in K, it also gives you M. Is M plus M equal to 2M? Yeah. Last one here, G bracket M. Well, we just had that problem a second ago. You can't actually do G bracket M because that implies that you want to find the Y value when given an X value, but M is the Y value. You're not supposed to be plugging in a Y value into this notation. So that also doesn't really make sense. This one's kind of tricky because you really have to understand like your notation and how that's supposed to work. Any questions on that one? Here's a graph of tan. Where are the asymptotes? Oh, so here's the first asymptote. What's that value? Yeah, half of pi. Here's the next asymptote. Where's that one? 1.5 pi. The next one, if we drew it, would probably be at 2.5 pi. So which one of these statements represents the asymptotes properly? D. You have an asymptote at pi over 2. The next asymptote is pi away. But you could add pi a million times if you want. You could add pi once or twice or 3 or 4 or -5. That makes sense. Okay. Here's another one. So this is a graph of, looks like part of a sine graph. We don't get the whole graph, we get part of it. And the question says that we could try to write it as a sine b theta minus c d. What does the a value do right here? This is an up and down. The d value slides the graph up. This c value moves the graph side to side. And the one that we care about, the b value, what does a b value do? Squishes it in, or possibly pulls it out. It's like the accordion of the slinky kind of thing. Our job then is to try to calculate that b value. B really affects period of a graph. What is normally the period of a graph? For sine, it's 2 pi. I'm just going to write that out here. The period of a graph of normal sine would be 2 pi. Now my question is, what's the period of this graph? It's kind of tricky to figure out, but I would say that this point right here and this point right here seem to be like you kind of carried the graph on. Seem to be the kind of like start and finish. So where is this part right here? And where is this part right here? What was that? 6 pi? I'll just double check here. This is a 2 pi over 2. And this is 14 pi over 2. So that would be 12 pi over 2 in between them all, which would be 6 pi. Is that okay with everybody so far? The period of this graph is 6 pi? Well, normally a graph's supposed to have a period of, I'm just going to use my hands here, 2 pi. Now the graph has a period of 6 pi. What happened to the graph? It got 3 times bigger. How do you make something 3 times bigger? Do you put the number 3 there? You use 1 over 3. If you put 1 over 3 right here, it actually pulls it out 3 times as much. If you put the number 3 there, it would squish it in 3 times as much. So 1 over 3 is the number there. It wants it to the nearest hundredth. So 1 over 3 is 0.3 repeating. So the right answer would have been 0.33. Is this stuff you guys could do? I know it's kind of still early, we just started the unit, but is this stuff you guys at least you can follow?
Yeah.
Okay, last one, then we'll call it a day. Here's a graph, and here is a second graph, and we want to try to figure out which statement is true. So before I even look at the statements, I just want to talk through what's happening. This a value right here makes the graph taller, and this b value right here could possibly squish the graph. Well, now we have a different graph. It's got a k value. It could also make the graph taller. We've got a b value, which could squish the graph in or out. But this one has an extra value. It has a c value, which could slide the graph side to side. So let's read through all 4 statements, see whether one of them seems to make sense. Do both graphs have a period equal to b? Actually, that is a really good distractor, but that's not true. What is the period of a sine graph? 2 pi. Now, whatever this b value is right here, that's either going to make the graph get squished in or pulled out. So hypothetically, let's say that value there was 1/2. Then the period would become 4 pi. Is the period itself actually whatever the b number is? No. They both have the same period, because whatever this number right here is and whatever this number right here is, they're both going to either squish the graph in or pull it out. But the period itself is not going to actually be what the b number is. The b number just stretches or squishes. So a is a great distractor, but not true ultimately. Okay, y-intercept. Where is normally the y-intercept of a sine graph? 0, yeah. Now, what's happened to this graph right here? We've made the graph taller. Will that affect the y-intercept? B value, will that affect the y-intercept? Okay, this graph right here then has to have a y-intercept of 0. This graph right here, k, Well, k will stretch the graph up and down, but will the y-intercept move? No. The b value is going to stretch the graph in and out. Will that change the y-intercept? Okay. This minus c is going to shift the graph over. I don't know how far it's going to shift the graph over, but let's say it shifts it this way. Now will we have a different y-intercept? Yeah. But is it going to be a minus k units lower? I don't feel like that is necessarily helpful yet, so I'm going to leave that one for now, because although it's going to be a different y-intercept, I don't know that that proves anything. So I'm going to leave that one for now. Let's talk about the x, the theta intercepts. Where are the original theta intercepts? Well, I'd say they're supposed to be 0 and pi and 2 pi. What's going to happen when this guy has a minus c? What's that going to do to the graph? It's going to slide everything that way. That's actually what c says. The theta intercepts are going to be c units to the right of the other ones. That one is true, because that's what that minus c does, is it shifts the whole graph right. The last statement I guess we could talk through. The y-intercept of the g graph is k. That's not true. I don't know what the y-intercept is going to be because of the fact that it's been slid over, and we don't actually know how far it's been slid over. But definitely the y-intercept of the first graph is definitely not a, because the graph is normally like this, and a means that you pull the graph up and down. But the y-intercept was at 0. If you pull the graph up and down, it's still at 0. So really the only answer I know for sure is that c is true. This minus c here slides the graph right. Okay, I'll stop now. Any questions? All right, so here's what we've covered then. You guys should be able to work with radians and degrees. Actually, you know what? This is probably worth a second just to show you curriculum outcomes. Give me 1 second. There are 6 outcomes for trigonometry. Here's the first outcome. Do you understand angles in standard position, and can you work with radians and degrees? That's pretty much what we did the first day or so. Second one, do you understand how to use a unit circle? Third one, we're kind of starting on a little bit. Can you solve problems in radians and degrees using angles? It's kind of vague, this one here. But we've kind of started doing this. And then this one here, can you tell me what the graphs of sine, cosine, and tangent look like? Can you graph and analyze them? So it doesn't actually say that you need to know cosecant, secant, and tan, but I'd like you to just know them anyways. And then the last 2 we actually haven't covered yet. Do you guys know how to do radians and degrees? Do you know how to do a unit circle? Do you know what graphs look like? And can you start solving things? That's basically our outcome so far. Okay, I'm done. I talked longer than I thought I would. You guys can go take a break.